My name is Babjak. I'm from Vanderbilt University, and today I'm very briefly going to talk about my research, which is about the analysis and efficient onset time detection of acoustic emission signals with power constraint sensors like this one. Alright, so in a nutshell, I'm going to talk about a structural health monitoring technique using acoustic emissions. We are using a wireless sensor network approach for this, and I'm going to demonstrate our prototype system, which we tested on metal beams with 2 channels, and we used a very simplistic time difference of arrival method here. Our 3 main contributions is the actual sensor itself, an efficient onset time detection method, and an efficient false positive rejection. So what is structural health monitoring? Structural health monitoring is concerned with the inner state of huge structures like wind turbines, bridges, or buildings. Now, I just recently learned this term, and I think it very accurately describes this field. It's the science of signatures. And in our case, we're using a phenomenon called the acoustic emission. And this describes the phenomenon that when materials break, there's a sudden release of energy in the form of ultrasonic waves. Now, that you can measure, and based on that, you can then infer the inner state of the structure. And our concept for this is a permanent sensor network that's deployed on the structure, giving the real-time state inside the structure. So I was talking about measurement. So in our prototype measurement, all the setup pretty much looked like this. We had the beam, the metal beams in the middle, which we would then break. On both sides we had mount. In the middle we had an industrial electromechanical shaker, and the beam was partially sawn in the middle just to give a definitive crack starting point. Now, on the 2 sides we had acoustic emission microphones, but at different distances. We tested not 1, but actually 3 metal beams, 2 aluminum and 1 steel. The measurement sessions lasted 10 or 20 minutes. We gradually increased the shaker's amplitude and then recorded all the raw data. Now, for this we used our custom designed measurement platform, which I have brought along. It's right here. If interested, I can show you this later on after the presentation. So it is made up of 3 parts. The one on the bottom is responsible for the power. It can work from various sources like battery or energy harvester, or you can either plug into the wall. The middle part here is responsible for the high throughput computations. It's based on the Smart Fusion Flash FPGA technology, and the top part here is the sensor part. It has some very minimal baseband capabilities and a radio frequency chip. Now, this is the analysis itself for the prototype. In this setup, we use the platform itself only to stream raw readings to a laptop where we did the actual analysis. Now, this is a very busy figure, so I'm going to break it down for you. So at the top, you see the beam that we were breaking. On the 2 sides, we have the acoustic emission microphones. And first, we start out with the analog signal processing part, which was kept to a very minimum. It only does some very basic signal conditioning, and then the signal gets sampled at the rate of 750 kilohertz at a resolution of 10 bits. Once we have digital samples, within the FPGA, we take these samples and put them in frames. These frames are then streamed through USB to the PC. Here we do a pre-selection. So, first of all, we extract the samples from the frames, then do some minimal filtering just to get rid of the low frequency noise. And then we have a threshold detector. Now, every time the signal crosses this threshold, we take a rough time window around this event. And any analysis is done on these time windows. The first type of analysis is a simple time frequency analysis, for which we use wavelets. The second type, the more elaborate, is a parameter estimation, and I'm going to be talking about this. So here we have two main objectives. I'll start with this one. So we have the time windows, and first of all, we want to figure out that within this time window, when did our signal start? When did it happen? That's number one. Number two, we want to figure out if that was a good, valid measurement or not. And for this, we use a utility function approach. So we define a function, a fitness function, a utility function, which is going to give a minimum right where the signal started, but also it will indicate whether the signal was valid measurement or not. Now, once we have that, then we can move on and classify these signals. Here we use a Gaussian mixture model, but I will get into that later on. So what is a utility function? How do you define it? Well, in the literature, what you will find most often is the Akaike's information criterion-based method, which was originally meant for autoregressive signal models, but the simplified version, which is widely used, that pretty much dropped that in favor of just comparing energy levels. And the way it does that, it divides this time window into two parts. The middle point is sliding. This is how it's calculated. N1 means the number of samples in the first part of the time window. Sigma 1 is obviously the variance in the first part. N2 and sigma 2 are the same for the second part. What's the problem with this? The problem is that it's based on a natural logarithm, which is not trivial to calculate on a resource-constrained embedded platform. So we came up with our own approach, which is simplified. Here we have basically, I didn't do it. I swear I didn't do it. Yeah. So we have this equation here, same variable, same principle, but we drop the logarithm. Okay, so these are the results. On the left side, you can see the Akaike's information criterion-based approach. On the right side, our approach. Up here is an actual valid measurement that we took in the time domain. And you can instantly see the problem with these signals, namely that they are highly dispersive. And it is very difficult to pinpoint the time when it started. Now here you can see the utility functions, and both are looking actually really good. They have a definite minimum point, although there's a slight disagreement where the signal started. But nevertheless, we have onset time. So now we move on to provide a quality index for the measurement. And for this, we used our observation that for a valid measurement, after the minimum, the utility function increases very rapidly. So if we take the derivative of these signals and we sum a couple points, let's say 40 measurement points, right after the minimum, then we should, for valid signals, come up with a really high value. Now, based on that, we have now a two-dimensional measurement space. The x-axis stands for the time difference, and the y-axis stands for the measurement quality. This is how it looks. Again, left side AIT, right side technical. Now, let's start out with this huge group here. So these points represent the measurements that we took in one measurement session. And on the bottom here, we see false positives. So this is when our threshold detector triggered, but this is actually not a valid measurement. It's useless. It's probably noise. What I want you to direct your attention to are these groups up here and there. Now, first of all, let's start with this. This group of measurements originates from the crack itself. And here we could model this as a Gaussian distribution and find the time difference. Now, with that time difference and sound speed propagation estimates, you can then calculate the crack position. In this particular case, the crack was located at 78.7 centimeters, and as you can see the results, we're pretty close. Usually, however, we find that we are off by 10 or 15 centimeters. But let's go back for a second. This group here, however, that surprised us. This was really unexpected. This originates from the crack that we have prepared. This was not expected. So that's when our time frequency analysis comes in very handy. And we looked at these two groupings. On the left, you can see the signal that originated from a crack that we wanted, and on the right, you can see a signal from the other group. And as you can see, they have two completely different time frequency signatures. So probably what we have found is an unintentional second crack, and there's a strong indication that this was outside the beam, actually in one of the mounts. And that's it for me. Final remarks. It was an NSF-supported research, and everything that you have just seen, each and every file is online and open source. And if my browser windows are still up, then I can actually show that to you. So this describes pretty much what I just told you in detail. And if you're interested in the CAD files, you will find them. That's it. Thank you very much.